record. All right, recording is rolling. It's Friday, May 5th. So yeah, last couple days, you guys have had substitutes, giving you guys some FRQs. Those solutions are posted, right? You guys got the AP exam here in a few days on the 11th. Okay? So here's what we do. We're gonna run this practice problem, the set of questions, right? And then about the last 50 minutes of class, got some guest speakers from UCF, actually a former AP student of mine and one of his colleagues. I'm gonna tell you guys about nanotechnology, so you guys can see some like science applications of things you guys can eventually do with this. Okay? All right, so since I've been running attendance, get some stuff set up, you guys have had some time to look at this. I want to keep things moving along here because I know got limited time. So look, classic double elevator Atwood. I got two masses, different different masses, right? Therefore, different weights. Okay. Right, so what is here? Let's run through the questions, then we'll go through this all. Right. First of all, what's the downward acceleration of the heavy block? This might be how AP phrases it. Right? Like one's going down, one's going up. But they have the same magnitude of acceleration. Right? What is after so much time has passed? What's the speed of each block, and how far has each block moved? Ooh, that sounds kinematic. Right? So we got dynamics, we got kinematics. Notice I gave you a massless frictionless pulley. They might call that an ideal pulley. Okay. And then, okay, so we got unit 2, we got unit 1, and then set up a conservation of energy equation for the two block Earth system, so block Earth system. Hey, that sounds like unit 4, conservation of energy. And then I got one more question I've got partly covered up here. So, all right, first question: who solved the downward acceleration of the heavy block? Yeah.
45 minutes to bring second.
Let's check that out. Okay, so let's walk through that. Okay. So you might do a free body diagram on each block, right? So this block, guys, what's the weight of this block down? 30 newtons. Yeah, let's just use gravity as 10 meters per second squared. We usually round it down. What's the downward force on this block? Yeah, 10 newtons, right? Notice that this is about a third of this, right? Or it should be 1/3, right? This is a third of this. Okay. Ooh, is there a tension up on each block? Yeah, do you think that tension is greater in magnitude than 10 newtons, but less than 30 newtons? It's kind of a middle value, right? Is it the same tension on each block? Right? I'll call it F sub T, the tension force. Right? Hey guys, the tension force, that's just internal to the system. Okay? So the external forces are the ones I care about. Don't I care about these external forces right here? Okay, guys, that. Okay. All right, so let's see. Now, one way you can solve this, some textbooks and some, like when some of you guys can take physics in college, what some instructors do is they set up a system of equations where there's a weight and a tension on this guy, there's a weight and tension on this guy, and they set up two equations. And the two unknowns would be the tension and also the acceleration. Okay. I'm just gonna, since this is review, I'm just gonna do the way I usually do it with you guys, which is look from a macro point of view and say, well, these are the external forces driving the entire system. Isn't acceleration net force on total mass? Would that be true? Right. And again, from a macro point of view, how I usually take you guys through this one. Right. What is the net force? 20 newtons, right? Because 30 newtons minus 10 newtons. We got 30 newtons saying let's go clockwise, and 10 newtons saying no, let's go counterclockwise. Those are pulling against each other, right? Okay. Guys, how much total mass is being moved? 4 kilograms, right? 3 kilograms plus 1 kilogram. Wouldn't that be true? Just like that, right? So, in general, it's the difference in masses over the sum of the masses times the gravity field of the planet ends up being the same thing, right, in terms of variables. Right? Let's run the numbers here. So we got 20 newtons acting on 4 kilograms. Is that called 5 meters per second squared? Right? Right. Rule of thumb: whenever these two blocks on the Atwood are a ratio of 3 to 1 in terms of mass, it moves at half the rate of the gravity field. Okay. Okay. You guys get there? Right. Okay. So that's the first one, the acceleration block. Next question. So that was a unit 2 question, right? Dynamics. We just solved that. Okay. Next pair of questions are kinematic. What's the speed of each block after so much time, after 3 seconds? Guys, what's the formula I'm going to write to answer that? V equals AT, right? You guys are thinking? Or maybe you remember this version. VF equals V naught plus AT, right? But if it starts from rest, I should have said start from rest, but let's say it starts from rest, right? Right. Okay. So we've got 5 meters per second squared. We're doing 3 seconds. You guys see 15 meters per second? It's picked up to 15 meters per second. You guys see that? Right. Next question. How far has each block moved, right? I mean, one's going up, one's going down. So like this, guys, what's your distance formula in an accelerating environment? 1/2 AG squared. Exactly. Right. Again, you might think, well, what about the V naught T plus, right? But if it starts from rest, then that just goes away anyway, right? So we got 1/2 times an acceleration of 5 meters per second squared for a time. Remember, 3 seconds. Square that. Let's see what we're getting here. We got 1/2 times 5 times 3 squared. That's 22.5 meters. Right? Let's say this is a giant Atwood. It's like several stories tall, right? If it was allowed to go along that long, right? Okay, guys get that? I'm trying to. Right? Okay, right. Everybody good so far? Right? You guys can solve all these. Now let's switch gears and think. Let's switch frameworks to Unit 4, conservation of energy. Guys, everybody write down on your paper in your notes. Right? What is the conservation of energy equation for the 2 blocks in the Earth, right? The block Earth system? Okay. Give you guys a little head start here. Okay. All right. So I'm going to start writing the solution. Again, I want you guys to stay a couple steps ahead of me. Sum of energy initial equals sum of energy final. Okay. I mean, this would make a really good FRQ question, right? Because involves a bunch of parts of physics, blah, 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 nice checklist of points. Okay. And so, all right, here we go. What's supplying the energy for everything to move? Okay, yeah, but where's that kinetic energy coming from? Because it starts at rest. Yeah. The potential energy, and which block is falling that's allowing the whole thing to move? The 3 kilogram block, right? Maybe I'll call this here. Let's call this like mass A and mass B, for example. So if I were in terms of variables, I'd say like mass B is going to fall. Right? So what's the energy form of this? mgh. Right? Now the height is like the height it's moved. So right after it falls some height, right, equals right. Now where did that energy go? Kinetic. Right? And they each have a kinetic. So that's your 1/2 mass A V squared plus 1/2 mass B V squared. Okay. But also one other place, which is what? Exactly. It had to lift this block. So it did some of the potential energy went into lifting mass A. Isn't that true? Just like that? Okay. That's in terms of variables. Let's pop some numbers in. Well, anyway, here. Actually, that's a conservation of energy formula for that. Let me just uncover this last question because I want you guys to solve something. So I need to give you guys one more number before you can solve anything. Okay. Using your conservation of energy equation, determine the speed after moving 22.5 meters. Hey, 22.5 meters. That's exactly the target distance we're interested in. So what does the answer to this question have to be? What's the speed after that distance? 50 meters per second, right? And how much time did it take to get there? 3 seconds, right? In 3 seconds, it moved this far, this fast. And now remember, conservation of energy, I don't see anything about time in this equation, although time is taken along in the background. Okay? But this is a different perspective to also get to the same solution. Okay, you guys remember that? So let's pop some numbers in. Mass B, I've got 3 kilograms. So we got this 3 kilogram block. Let's go ahead and use 10 meters per second squared. Okay. We got, we got 22.5 meters. Okay. And where'd that energy go? So 1/2 times mass A is 1 kilogram. Right. We're solving for this V being squared plus 1/2 times 3 kilograms times the same V squared. Right? I didn't put subscripts on these because I could say V finally, but it's the same speed, right? One's going up, one's going down, opposite directions, but same speed. Okay? Plus 1 kilogram at 10 meters per second squared. And then it's moved up 22.5 meters, right? This one was at the height of 22.5 meters, went down to 0. This one was 0, went up 22.5 meters, right? That's one way to think of it, right? There might be different ways you could shuffle this around and think about it, but if you shuffled anything around, you end up with negative signs. This is the way this is the way I usually do it with you guys. Okay? And so let's see, what is 3 times 10 times 22.5, right? I'm looking at 675 joules of energy. Oh, I should have asked you guys what unit that would be, but you guys would have said joules, right? We're talking about energy. Okay. Is equal to, see, it got 1/2 V squared plus 3/2 V squared. What's 1/2 plus 3/2? Okay. So I can combine these two terms. Is that okay? And just call it 2V squared. Maybe I'll throw in an extra step here. 1/2 plus 3/2 of v squared, okay? And then plus 10 times 22.5 times 1. We've got 225 joules here. Okay, so these are kilograms. Okay, all right, you guys see that? Are we good? All right, so we're just a couple of algebra steps away. Again, you guys know what the answer is going to be. You guys just told me. So I'm going to subtract this energy over here. Oh, right. Here you go. Yeah. All right, so subtract this over. But 675 minus 225, right, looking at 450 joules is equal to, just go ahead and combine these two fractions, 2 kilograms times v squared, right? You guys got that? Okay. Divide down 2 kilograms, 450 divided by 2 is 225, right? So v squared is 225. Okay. Now joules per kilogram is like meters squared per second squared, okay, which is good because take the square root, right? You guys, what's the square root of 225? 15, and the unit is meters per second, which is exactly what you guys told me it was going to be, because you solved it already using unit 2 dynamics and unit 1 kinematic motion in combination with each other, right? Or if you like, unit 4 conservation of energy, get the same answer. Okay, all right, you guys good there? You guys can do that? Okay. All right, any question? Any question? Okay. All right, so I know we're going into the weekend. Remember, there's lots of review materials out there. Let me remind you guys, there's a bunch of review materials on Google Classroom. If you look back at like midterm or when we started the review a few months back, I posted a bunch of review links, posted some to like Flip and Physics and some, there's some YouTube channels. There's a guy named, let's see, Bozeman Reviews, right? No, it's, I think Bothwell STEM, right? Anyway, there's a bunch of links, right? Guys will go through like AP FRQs questions, right? If you look at AP Classroom, there's a bunch of review videos there. I've also posted a bunch of like extra FRQs, right? You've also got the solutions to the FRQs you guys been looking at last few days. Yeah, there's just anything class, like so many, like everything we've done in class, you guys know is on Google Classroom, right? You guys got that review there. You guys got the textbook. You guys got all the review materials here. Where is, right? You guys remember this right here, like this page, all the review pages I've given you guys. Okay. All right. So, right, so you guys got plenty of stuff you can do there.